So I guess I should be looking there and maybe there as well. So what a joy. I mean, I don't know how I should put this, but we met many years ago and you look exactly the same. I won't mention how many years ago.
You must have forgotten what I looked like then.
I was a doctoral student, and you was telling me that I thought you were a doctoral student too, but in fact you were only a master's student. And we met in Wisconsin with the great Richard Davison, who of course has pioneered, and I'm sure he will come up in your talk. Well, he's been very interested in meditation and is a good friend of the Dalai Lama, I believe, amongst many other things. Richie, as he's known to his friends. But I think what has gone on since then is that you've really, I think, pioneered our understanding of meditation is not just meditation, but really thinking about how that could work with the predictive mind. And it's been so wonderful. So I think what has been wonderful is to be able to follow your work from afar, and now you're here. And now we're going to pick your brain and we're going to learn a lot of things. And so that's very exciting. So please, everyone, welcome to Heleen Slagter.
Well, thank you very much for a very nice introduction, and also for this invitation to present some of our ideas and work here today in an unrestricted talk. I've never had the opportunity to give an unrestricted talk, and I've tried to constrain myself because I could talk about this for hours or days, but I think it will be about 90 minutes without questions. So if you have many questions, maybe longer. So if you have to leave earlier, please don't feel offended. And hopefully there will also be time to chat more after my talk. Meditation and the plasticity of the predictive mind. So in my talk today, I think I want to drive home 2 points. And the first one is that, is that learning is a much more pervasive feature of human cognition than we typically assume in mainstream cognitive neuroscience. So we typically think about cognitive control processes, goal-directed cognition, for example, selective attention or planning, imagery, working memory, as deliberate processes that are sort of abstract and general and can operate sort of independently from the information that they actually latch onto. But what I want to show in the first part of my talk is actually that these deliberate goal-oriented cognitive processes can actually be constrained to behave, to operate in certain ways on the basis of our past experiences. And I want to use some of the work that we and others did in the domain of selective attention to sort of demonstrate that point. And then in sort of an intermediate part of my talk, I want to talk about the framework of predictive processing, because I think this generic theory of our brain can actually very nicely account for some of these observations. And it also provides an introduction to some of the work that Morten just alluded to that we've done on meditation. Because over the past few years, we've put forward the notion that what meditation does is not so much boosting our cognition, enhancing our attention, but that at the most fundamental level, it's actually aimed at removing or reducing these automatic constraints on human thought, on our thought processes. And so maybe a lot of you are already familiar with predictive processing. But you should just bear with me in that intermezzo, because I think it's sort of necessary. It provides necessary background also for the second part of my talk. So the example of selective attention. So selective attention is traditionally defined as this mental spotlight that we can top-down direct at will at any information that is relevant to our current goals. And as such, attention can control what information is deeply processed in the brain and what information remains largely in the dark. And indeed, over the past several decades, a lot of work has shown that attention actually acts as a sensory or perceptual filter. And that has been shown using tasks like this. This is a Posner cueing task whereby participants are first presented with an attention directing cue. In this case, it's a spatial cue, attend left, and this is a covert attention cue. So people have to keep fixation and then covertly attend to the left. And what this research has shown is that when, after some interval, a stimulus is presented and it occurs on the left, so it's attended, that then early visual processing of that stimulus is enhanced, and that's then also associated with better performance. Compared to when you have that same stimulus also presented on the left, but your attention was directed elsewhere. And what this work has also shown, and this is actually also stuff I worked on during my PhD, is that if you look at this interval between the attention directing cue and the stimulus, that there is this network of frontoparietal regions that is involved in the directing of attention and that implements an attentional or sensory bias already before the stimulus is presented. So if you look at those visual regions that represent the to-be attended information, the goal-relevant information, you can see that their baseline activity is already enhanced prior to the presentation of the stimulus. So in this sense, attention can act as a filter, resulting in a prioritization of the processing of those things that are relevant to our current goals. But in more recent years, there's this growing realization that what we pay attention to is not just simply actually guided by our current goals or by things that are salient in the environment, but that how we pay attention is often strongly guided by statistical learning or learning grounded in statistical structure in the world. And so in other words, that learning is a much more pervasive feature of how we pay attention than traditionally assumed. And just to illustrate this, I want to show you data from a study by Young et al. Already done in 2013. They had participants perform a visual search task like shown here, and they had to find a target, a letter T, and then indicate its orientation. And this letter T was presented in a cloud of L's that were oriented in different ways. So it's sort of a difficult task. And critically, what they did is they presented this target letter T much more often in one of the 4 search quadrants. And what they showed, and actually what already other studies have shown before them, is that when you introduce such a spatial regularity, that participants quickly pick up on this. So their search times are much faster whenever the target occurs in this highly probable quadrant compared to when it occurs in any of the other probable quadrants. And you can also see that this predictive bias sort of gets bigger over time. And it's important to point out that subjects are largely unaware of this regularity. So if you ask them afterwards, if you have to indicate in which of these 4 quadrants the target occurred more often, at the group level, people are at chance or slightly above chance. So most people do not pick up on this regularity. It's a form of implicit learning. So your attention is implicitly and automatically biased based on this regularity in the world. And why I'm showing this data is because they actually had a second phase in their experiment where they removed this regularity. So now the target could occur equally often again in all 4 search quadrants. And what they showed is that this attentional bias persisted. You can see that here. So even after another 24 blocks of this task, participants remained faster. Their attention remained biased towards that search quadrant where the target used to occur more often in the environment, but no longer occurred more often. And so these effects of statistical learning on attention are very persistent. And so this is one of the studies that shows that learning is a much more pervasive feature of attention than we typically assume. And also that learning just develops automatically, implicitly, and is also highly persistent. And so what that shows is that what was relevant for goal-directed behavior in the past can bias our future attention to automatically behave in certain ways. And so that goal-directed attention can be automatically constrained by past experiences to operate in a specific way. And when you think about attention in daily life, I think our attention often operates very automatically in daily life. If I have to find my bike keys, my attention often automatically goes to the cupboard where I often place them when I enter my house. And it's not until they're not there that there's this huge prediction error, like, oh my gosh, where are my bike keys? And then this very effortful search ensues. And so there's also adaptive value to developing these attentional biases. More recently, it has been shown that also statistical learning about what is irrelevant or distracting can similarly drive what we subsequently ignore in the future. And that also has adaptive value because that can reduce the influence of distracting information and also facilitate performance. And to illustrate this, I want to show you some data from a study by colleagues at the VU, Jan Theeuwis and his former PhD student Benyi Wang. They had participants perform this visual search task here. I don't know if you can see it well on that screen, but basically in this task, people have to find the unique shape. In this case, it's a circle that's presented among diamonds, and then indicate the orientation of the line element in that unique target shape. And then on 2/3 of trials, one of these non-target shapes can actually have a unique color. And you can see that's a highly physically salient stimulus. And indeed, what many studies have shown is that because it's so physically salient, it automatically grabs your attention. So in the trials where this so-called singleton distractor is present, you're actually slower in finding the target because your attention was captured first by this distractor. And what they did in their study was that before the onset of the search display, they actually presented participants with a distractor cue that informed them about the upcoming likely location of the distractor. And what they showed was that participants were not able to proactively use that distractor foreknowledge to prevent distraction, because they were equally slowed down in their response by the singleton distractor after a valid distractor cue as compared to after an invalid distractor cue. And so it's very difficult to proactively suppress or prevent distraction. But they then showed that if you simply introduce the spatial regularity, when you present this singleton distractor much more often at one of the search locations, that this greatly reduced distractor interference, and that's shown here. So whenever this singleton distractor occurred at this highly probable location, search times were much faster compared to when it occurred at any of the low probable distractor locations. And in fact, search times were almost as fast as in the trials where this singleton distractor was not present. And so statistical learning, predictive learning, seems to be in particular critical to our ability to ignore distracting information. We need to gain experience with it, and then we can learn to safely ignore it or learn that it's not relevant to the task at hand. And so in my lab, we've done a lot of work looking at how statistical learning actually biases our attention in automatic ways. And I don't have much time to go into that today because I want to get to the other parts of my talk as well. But basically what our work, but also other studies have shown is that what happens as a function of statistical learning is that this sharpens these pre-stimulus attentional biases. So neural populations that represent expected likely information start to more sharply represent that information, and that then prioritizes or drives your attention to automatically prioritize the processing of that goal relevant information. But when the learning concerns irrelevant stimuli or learning about distractor stimuli, we see something very different. We either see that there's no change before the information is presented in how it's being represented, or that the learning transforms the representation of the expected distractor input in a way that's different from how we find enhanced tuning towards goal relevant information. And if you want to know more about this work, you can read some of our papers that we've done on this. But the point I just want to make here is that that we and others have shown that statistical learning differentially affects the processing of relevant versus irrelevant information, and that then ultimately leads to a biasing of attention towards those things that we've learned are likely relevant. Another thing that is very interesting about this is what I want to talk about next is so far the assumption has been that what statistical learning does is that we learn about regularities in the environment. So we learn where we can likely find something important and where likely distracting things happen or what likely distracting things look like. And indeed in daily life, a lot of our attention is environment guided. So if you walk into any bathroom, when you want to find the soap, you can use the contextual layout of the bathroom to find the soap. It's typically found at sinks. And so in daily life, our attention is often guided by contextual information. But we also know that the brain can represent information in different frameworks. So we can represent information in a world-centered way. So independent from where you are in a particular room, in a particular bathroom, you can represent that information, but we can also represent it from our own perspective. So where things are in the world with respect to where we are, and that's called an egocentric reference frame. And it makes sense that we have an egocentric reference frame because in order to interact with the world, we of course also have to know how we can act upon the world, right? If I want to grab a particular object, you need to know how you move your arm to grab that object. And indeed, our visual motor system is egocentric in nature. So it's organized with respect to our own bodily coordinates. And interestingly, there is some work that has shown that the native coordinate system of spatial attention is also egocentric. So we often think about selective attention as some abstract process. But when you think about it, when you apply your attention in the world, it's always with respect to where you are. I cannot attend to that object unless I sort of know how I can potentially sample it from my perspective. And so that makes sense. And just to show you again some data that I showed this as work again by Young et al. 10 years ago. Here they had participants do the precise same visual search task. So they again had to find the target letter T, indicated orientation, and unbeknownst to the participant, they presented this target much more often in one of the search quadrants. And then they replicated that finding that I just showed you, that search times were much faster whenever the target occurred in the likely quadrant compared to any of the unlikely quadrants. But then what they did in the training phase was very interesting. I didn't mention this yet, but in this particular study, they actually had people stand next to a table and the display lay flat on the table. And so in the second half of the experiment, in the test phase, they actually moved participants' standing position with 90 degrees around the table. And they again took away the target regularity. And so that created 3 types of search quadrants. One where the target used to occur more likely in the world. One where it used to occur more often from the perspective of the participant. So you see that here, bottom left, bottom left. And then there were 2 search quadrants where it never occurred more often from either perspective. And what they found was that this learned attentional bias actually moved around the table with the participant. So their attention was biased towards the search quadrant where the target used to occur more often from their own perspective. And so that seems to suggest that what statistical learning does is not so much learning about where regularities are in the world per se, but how you can sample the world with your attention to most likely find that relevant information. And so in other words, spatial attention, when we apply it, cannot be abstracted from the observer. It's in that sense embodied and also constrained by the observer's sensory motor processing. So it seems that next to a perceptual component, there's also an action component to spatial attention. But I think I see you guys thinking, it's like, but you know, we can also learn where things are in the world independent from where we are. It would of course be completely useless if we can only learn where things are with respect to our own perspective. And yes, of course, we can also do this. And Young et al., for example, also showed that when you make these spatial regularities explicit, so when you tell participants, you know, the target will occur much more often in one of these search quadrants, then actually the learning can become world-centered. And so explicit knowledge seems to allow us to sort of abstract ourselves away from, you know, who we are as an agent and think about things from a world perspective. And the examples I just gave with the bathroom, of course, you know, in a sense, this also relies on explicit knowledge because we know that soaps are typically found at sinks. Yeah, and you use that information when you look for the sink. And so this is not an implicit search task in that sense. And last year, Li-Tian Chen, who's a PhD student in my lab, tried to extend this work to the domain of distractor learning. And so here the question was, learning to ignore distracting information, is that also viewer-centered, egocentric? And so we had participants do one of these additional singleton tasks that I just described, where people had to indicate the line orientation in the unique shape in the target. And then on 2/3 of trials, one of the non-target shapes had a unique color, so it was a distractor. And unbeknownst to the participant, we presented this distractor stimulus much more often in one of the 4 search quadrants. And we had participants also do this standing next to a table that had the display lay flat. And then in the training phase, we replicated our initial finding that search times were faster whenever this singleton distractor occurred in this highly probable search quadrant compared to the other ones. And then we did the same thing as young adult did. After the training phase, we moved participants around the table by 90%. We took away the distractor location regularity such that there were 3 types of search quadrants, one where the distractor used to occur more often in the world, one where it used to occur more often from the perspective of the participant, and then 2 search quadrants where it never was more likely from either perspective. And lo and behold, we also found that distractor location learning was viewer dependent. So statistical learning can also bias how you will not move your attention or how you suppress attentional sampling in space from your own perspective, and not where distractors are in the world per se. One of the other things we did is in some follow-up experiments, well, maybe you can say, well, when participants are always standing on one side of the table and the distractor comes here, maybe the viewer-centered learning is just easier because, you know, you have a fixed position. It's not like you're moving around in the world. Maybe when you're moving around in the world, that will force you to learn in a world-centered way. And so maybe, you know, this was just a too static kind of environment for world-centered learning to occur. And so we also did another experiment 2, whereby at the start of each trial, participants saw these 2 feet, and that indicated on what side of the table they had to stand. And so in this trial, they were standing here, they did the visual search task, and then in the next trial, the feet could occur at any of the other sides or remain on the same side. And so during the training phase, during the learning, participants were continuously moving their standing position around the table. And then critically, there were 2 groups. I see the OneDrive icon. That's so annoying. Wait, let me see if I can get it away. Is my cursor there now?
Don't see it online.
I know, but we have an audience here too. There we go. Yeah, that's better. And so critically, there were 2 kinds of groups. There was one group in which this highly probable distractor location moved with the person around the table. So it was probable from their own perspective. And in the other group, it was fixed in the world, but random with respect to their standing position from their view. And so the critical question now is, as participants are actively moving around during the learning, do we see that the learning maybe becomes more world-centered, or does it remain viewer-dependent? And basically what we found that even in this interactive setup, the learning, sorry, I lost my ability to move to the next slide. What happened here? No, where am I? I don't know what happened there. That even in this more interactive setting, the learning remained egocentric. So here you see 8 blocks of the tasks on the x-axis and search times. And in green here, you see the trials where there was no distractor. In red and yellow where there was a singleton distractor. And in yellow, it's when it occurred at the location where it was likely from the perspective of the viewer for the egocentric group. And you can see that search times then are much faster compared to when it occurred at any of the less likely locations. So here you see distractor location learning when the distractor was tied to the viewer's perspective, but random in the world. And in the world-centered group, you see that there's no learning. So here the distractor location is fixed in the world, but random with respect to the viewer, and there's no learning. And so this is in the case where the learning is implicit. We also manipulated in a third experiment whether or not this world-centric group had explicit knowledge about that this distractor occurred more often at one sort of side of the screen, so that it was fixed in the world. And then we see world-centered learning. And so here we also see that distractor location learning, what frame of reference you use during the learning is dependent on whether the learning is implicit or explicit. And so I think critically, what this shows is that implicit statistical learning can bias attentional selection in action space. So how the agents moves their attention in space, or suppresses how their attention moves in space. And that spatial attention in that sense cannot be abstracted from the agent, but it's also tied to action planning. There's this action component to it. And so I think what these data that I showed, but also larger literature, now sort of shows is that selective attention does not simply equate to a mere modulation of sensory processing, so facilitation of perception, but it also determines how we actively sample the environment and acquire new sensations. So attention also has this action component to it. It's not just a perceptual filter. And how we previously sampled the world influences also how we subsequently pay attention, but also what we ignore. And so that learning is a much more pervasive feature of selective attention than we typically assume. And importantly, this learning is grounded in the statistics of agent-environment interactions. It's not just about the perceptual regularities in the world, it's also about how you can sample the things that are relevant or prevent yourself from sampling the things that will distract you from a task at hand. And so in that sense, attention is really one of your most valuable skills because it determines how you make contact with the world. It optimizes agent-environment interactions, your relationship with the world. It guides what information we sample and process deeply, use to make decisions, guide actions. And importantly, also, what you pay attention to now automatically gates what you pay attention to in the future. And so you should really use your attention carefully. But I use this example of selective attention to sort of point out the fact that in contrast to long-held notions of cognitive, goal-directed cognition as something abstract, generic, that is completely operating independently from past experiences, from the knowledge that they latch onto. It seems that these deliberate goal-directed cognitive processes can be automatically constrained to behave in certain ways, implicitly. And in the case of selective attention, through this implicit probabilistic action-oriented learning. And so that then raises the question, how can we then understand this? Because these findings are difficult to reconcile with current theories of attention. And that's actually what brings me to predictive processing. So I don't know if there are any questions now or how you typically do this. Is this more interactive or whichever way you want it. If there are any questions, I can take them now or later. Yeah.
I have a question because I read a paper about egocentric and allocentric processing.
Yeah.
And they compare, it was a cultural comparison between people from Netherlands and Hayam. It's like an indigenous group.
Oh, interesting.
And what they found is that because Netherlands have more egocentric words they use in their daily life,
yeah,
they were better in a search task when the target was egocentric, and the Hayam were better when the target was allocentric.
Oh, interesting.
So
yeah.
My question here is whether you could also assume that implicit learning for distractors and targets and this persistent learning is also shaped by culture.
Yeah, well, that's what the data you mentioned seem to suggest, that there are cultural influences that can also affect how you learn about the world, whether it's more from your perspective or more in a world-centered view. I'd like to know what paper that is. Maybe you can share the link with me afterwards. I don't know
so
it.
Maybe that would be an interesting idea for follow-ups.
Yeah, it's very interesting. Thanks for letting me know. Yeah.
So, I mean, this idea of a spotlight is not a really good
analogy
at all.
No.
Because it seems like the spotlight has a mind of its own in a sense. And it's much more, I guess you may be coming on to this in predictive processing, more that the deployment of precision weighting has its own dynamics to do with this learning process, and
it's true. It's not simply about processing information, but it's also about generating information. So there's, yeah, but I'll get to it indeed in the, yeah. So predictive processing, yeah, I apologize for people who already know everything about predictive processing, but you'll just have to bear with me as I go through it. I am making some important points that I'll get back to also when I talk about meditation as a way to remove these automatic constraints on cognition. So predictive processing, I mean, it's said to be a unifying theory of the brain. It proposes that everything that our brains do is geared towards minimization of prediction errors. Whether that's the case or not is topic of huge debate. But I think it's clear that this framework has enormous explanatory power. And I think it also can better account for, like, the data, for example, I just discussed in the first part of my talk. And so predictive processing departs basically from the fact that our brains do not directly see the world, they do not directly hear the world, because the only thing that they have access to are the electrical signals that are conveyed by the senses. But the causes of those electrical signals are hidden to the brain. And so from this situation, automatically follows that our brains must build predictive models, generative models, about the likely causes of their sensory inputs. And then also continuously try to minimize prediction errors. So errors that occur when the predictions do not match the incoming sensory input, to ensure reliable models. And also then that, you know, learning is a much more pervasive feature of mental activity, of perception, because our brains must learn basically what the generative causes are of their sensory inputs, and thereby rely on statistical structure in the world and also the statistics of agent-environment interactions. And so it's clear that this, you know, puts the traditional notion of perception on its head. So the traditional view of perception is that perception is a largely stimulus-driven, bottom-up process of feature detection and evidence accumulation. But in this predictive processing view, perception is a process of top-down inference, in which our brains are continuously trying to guess what's out there. And then what is being fed up the processing hierarchy is not the sensory input per se, but rather the mismatch between the brain's a priori predictions and the incoming input, or so-called prediction errors, because only prediction errors still contain unexplained variance in the world that the brain did not account for yet. And so the brain's generative models are grounded in past experiences, so past learning about predictive structure in the world. And that this is the case, that perception is strongly influenced by learning, is very nicely illustrated by the hello face mask illusion. I don't know if you guys are familiar with this illusion, but I think it's very powerful. And what you see is a hello face mask that rotates around its axis. And just when you think you start to see the inside of the face, suddenly it just extends back outward and looks straight back at you. So you never get to see the inside of the face. And why is that? Well, there are actually two things that tie into this. One of them is that in daily life, we don't typically encounter faces from the inside. So we don't really have a strong prior for that. But the thing that even makes this illusion much more strong is that we've also learned over the course of our lifetime that light typically falls from above. And that then casts shadows in a specific way when an object is convex versus hollow. And the way the shadows are cast on the inside of the face is the way they would fall over an outward, how do you say that, a convex object. And that we have this strong prior, that, or hyper prior even, that light typically falls from above, is also very nicely shown by this image. It looks like this guy is just floating above a sidewalk. But when you look more closely, you can see it's actually standing on the sidewalk, and there's this whatever dirty oil spot or something on the sidewalk that seems to be a shadow underneath the person, and therefore it's floating in the air. But, you know, it's just an illusion of our hyperprior that light typically falls from above. So learning is a pervasive feature of perception also. But obviously our brains do not just make sense of sensory inputs just to perceive. They make sense of sensory inputs because they're part of a larger organism that needs to sustain itself in the world, and therefore must be able to give sensations meaning and also learn how it can generate the sensory inputs that it needs through action. And in fact, within predictive processing, bodily states also have to be inferred by the brain. Just like our brains do not have direct access to the world, they also do not have direct access to the body, but only only through these interoceptive inputs. And so brains too also have to learn how these interoceptive inputs are being generated. And importantly, within the predictive processing framework, the body is the first prior. At the most fundamental level, what our brains do is they expect our body to be in certain states that are viable for its survival. And so it expects certain physiological variables to be within specific ranges. We cannot be too cold, we cannot be too warm. There's an expectation that our body is well fed. And whenever these essential physiological variables are outside of their expected range, there's this prediction error. And in this particular case, brains cannot simply revise their expectations, their beliefs that the body is well fed, for example. When you feel hungry, for example, that, oh, yeah, no, okay, well, my body doesn't need to be well fed, because if it would revise that expectation, obviously it would die. And so this is a very stubborn prior, and therefore also the body is the first prior. And so how can it then resolve this prediction error that it's not well fed? Well, it can only do so by generating the sensory input that will actually bring the body back to its expected state through action, in this case through eating. And so actions are very important within the predictive processing framework, but because it's through action that we can actually confirm our expectations. We can generate the sensory input that we expect. And importantly, action also comes about through sensory prediction error minimization, just like perception, because we predict a certain sensory input, it's not there, and then we act to generate it. And so action also comes about through sensory prediction error minimization, just like perception does. And I think that's something really beautiful about the predictive processing framework. The other thing that's important is that's also through action that our brains can really learn about the affordances of the world. They can test their predictive models to what extent they're actually accurate. If I behave in this way, do I then indeed obtain this sensory input? So it allows for causal learning, but also how our own actions, how do you say that, change the world. And so it's really about learning the statistics of agent-environment interactions. And that also renders perception tuned to fitness, not truth. We see the world in that way as it's relevant to us. How we can generate, the inputs that we need, that's also how we see the world. And so our brains instantiate these models about how exteroceptive and interoceptive signals are generated. And it does so over different time scales. So it models the world and the body hierarchically, over different time scales and different levels of abstractions. And that also allows us, for example, to already anticipate future needs or future homeostatic needs. And in fact, I think we typically eat before we get hungry. I just did before this talk. I ate a bar because I knew I wasn't going to survive without eating for another 2 hours or whatever, 90 minutes. But importantly, at the most fundamental level, and this is a point I also want to make when I start talking about Buddhism and meditation, is that within this framework, perception and action are structured towards generating self-relevant sensory inputs that the organism prefers, that allow it to maintain its integrity and that allow it to align itself as best as possible also to its ego niche. And the term self-evidencing is also used in this context. We continuously want to confirm that we exist in the specific states. So there are a few important points to make. The first is that in this framework, the insight comes first, because our brains continuously create the reality, our own reality, from the inside out. But of course, the outside, the world, is also important, because what brains want to do is, of course, make sure that their models align with the possibilities for interaction for the world. but the internal comes first, and tickling is an example that's often used to demonstrate this, because why cannot you tickle yourself? Well, that's of course because when you tickle yourself, you already anticipate beforehand how your own actions are going to change the sensory input, and therefore the sensations are less surprising and are not experienced as ticklish. Another thing that I think is beautiful about this framework is that it also automatically ropes our sense of self into the framework. So to predict how our own actions will change the sensory input, we also have to model ourselves as a hidden cause in the world, right? Because when you think about how your actions are going to change the input, you also have to model how you are going to move around through the world. So you also have to model yourself as a hidden object in the world. And so that also renders our sense of self a construct of the brain, and something that is also intimately tied to the minimization of expected surprise, because it's about how you in the future are going to change the sensory input. That's always with active inference. There's always this counterfactual depth there as well. One other important thing to mention is the notion of precision. Because of course it would be detrimental if our brains would be simply at the whim of the world, right? So that whenever there's a prediction error, we update our beliefs, we update our models, because the world is full of statistical noise or uncertainty, and certain sensory inputs may also not be representative for the world at large. And so our brains must also deal with statistical volatility and predict how reliable or how informative sensory inputs are. Can we trust this new sensory evidence or not? And so it also has to estimate the precision, is the term that's being used, of sensory input, and that's a second order prediction. And so if you walk to the toilet at night and your couch looks brown, but in daylight it's red, you're not going to update your model of your couch that it's actually brown, because we know that in the dark, color information is low definition, it's not considered reliable, and so you give it less precision, less weight. And so this is a very important mechanism, because through precision weighting, only prediction errors that are informative, that are reliable, can actually lead to a revision of beliefs. And this way, our brains can actually control the relative influence of new sensory evidence over existing beliefs. So do we stick with our prior beliefs, or are we open to new information? And it's actually attention that has been set to map onto precision weighting, because the idea is that when a prediction error is assigned high precision, it's upregulated, so it can penetrate deeper into the brain. But when a prediction error is assigned low precision, it's actually downregulated, and it actually doesn't penetrate deep into the brain. It just dies out. And we know, I just talked about that, I think, in the second slide of my talk, that what attention can do is actually upregulate sensory gain. And so therefore, attention has been associated with this upregulation of, precision weighting. And this could explain this perceptual component of attention, this perceptual filter that we just talked about. But I also made the point that attention has an action component. So how can we reconcile those two things within the predictive processing framework? Well, I think the streetlight effect provides a very nice metaphor for understanding this, because the streetlight effect refers to the fact that if you lose your keys at night, when you start searching for them, you often first start looking in those places where there's light, where you expect to find reliable information, even though you may have just as well lost them, in the darker part of the sidewalk. And so we typically move our eyes to those locations where we expect reliable, unambiguous, or precise information. And so the deployment of covert attention precision to a given location automatically also biases planning or sampling, attentional sampling of that location. And in some recent papers, we actually talk about selective attention and inhibition from the perspective of predictive processing. So if you're interested in that, I refer you to that work. And another thing to realize is that within predictive processing, everything comes down to prediction error minimization. our brains model the world hierarchically across many different timescales of abstraction, including at levels of the hierarchy that are detached from the present moment. And when you think about it, a great deal of our mental life, we're actually thinking about things that are not currently happening in the world. We spend a great deal of time thinking about the future, planning stuff. If I go to the supermarket, then I'll do this and then I'll do that. Or if I would have sent that to my friend in the past, then maybe they would have reacted differently or something like that. And so we're continuously also, you could say, in a sense, estimating potential futures or different kinds of pasts. And it has been suggested that these temporary deep cognitive processes like planning, imagery, judging, episodic future thinking, that they can also be understood as minimizing prediction errors, but covertly, so sort of only in our mind's eye, but ultimately in service of future action. They allow us, in a sense, to execute as if hypothesis testing. And in that sense, they are mental actions. We think about how, we ourselves may generate certain outcomes, but only at these levels of the hierarchy detached from the present moment. And that's very interesting because here too, then we model ourselves in the narrative of our thoughts as a hidden cause of potential outcomes. And so also the narrative self is automatically roped into this predictive processing machinery, and our self is also hierarchically modeled. And so in the predictive processing framework, all mental activity comes about through these predictive models that have previously come to reliably reduce prediction errors. And that's a very important point, but because that automatically means that past experience or learning is a pervasive feature underlying all mental activity. And I really like this visualization by Martin Stacy et al. Of this process called canalization. That was a term that was introduced by Garrett Harris and Carl Friston. So canalization refers to the fact that, well, let me just explain what we're seeing here. So each pink dot is like a thought. And you can see as initial thoughts arise that they create a dent in our mental landscape, making it more likely that subsequent thoughts will actually follow the same trajectory through our mental landscape. And with more and more repeated thinking, you can see that this little dent actually becomes a canal. And so that's called canalization. So how we think now may automatically bias how we think again in the future. And a mind grounded in past experience is obviously adaptive because it aligns us with our eco-niche, but it can also be maladaptive. For example, if the environment changes, if we're no longer in a specific traumatic situation. Or when mental behaviors for some reason are too deeply carved, so we can only think in specific ways, but we're no longer flexible enough. And so our minds must be flexible to some extent. And that really then raises the question of the automaticity and plasticity of the predictive mind. Our brains must continuously balance, on the one hand, the precision they assign to existing beliefs and sensitivity to new evidence. So the precision assigned to new information from the world. A system cannot be too closed off, but it also cannot be too open. And so that's a tension that's really internalized at the level of the brain, as we've also discussed in this paper here from 2019. And talking about mental health being also at the center, it has been proposed basically that all mental disorders or psychiatric disorders can be reconceptualized as aberrant precision control, as either assigning too much precision to existing beliefs, thereby rendering the individual not sensitive enough to information from the world. So you get a misalignment between one's own beliefs and what's actually the actual reality, or assigning too little precision to one's own beliefs, being too sensitive to information, whereby one can be overwhelmed by the world. And Carl Friston actually said, if you think about psychiatric conditions, and indeed most neurological conditions, they are just broken beliefs or false inference, hallucinations and delusions. And so many papers have been published in recent years that reconceptualize psychiatric disorders as aberrant precision control. And one of the ones is on obsessive compulsive disorder, I was involved in that. That's why I'm mentioning it, of course. So obsessive compulsive disorder is characterized oftentimes by some dominant fear of anxiety. For example, my house is dirty and I can get contaminated. And this is such a strong belief that the person is no longer sensitive to evidence to the contrary. It doesn't take the evidence, for example, that their 16 hours of cleaning the house actually led to a clean house. And so they have to keep, cleaning their house. This one expectation dominates the landscape of potential actions. And in this paper, we actually talk about deep brain stimulation of the striatum, because Damian Denise, the last author on this paper, he's a psychiatrist, and he treats patients with obsessive compulsive disorder that are not sensitive either to medication or cognitive behavioral therapy with deep brain stimulation in the striatum. And what they find is that in many of these patients, deep brain stimulation of the striatum actually reduces these, how do you say that? Their obsessive cleaning of the house, or these obsessive compulsive symptoms. And the idea is what we put forward is that, it reduces the precision of this one belief, rendering patients more sensitive to conflicting evidence, and that then normalizes the landscape of possible actions. All right, so automaticity and plasticity of the predictive mind, that also brings me to meditation. And that's like the final part of my talk. Because there are actually striking similarities between how in actually Buddhism, the mind is being conceptualized and how it's being conceptualized within predictive processing. And so in Buddhism, a major premise is that our everyday experience is conditioned by past experiences. That's the notion of conditioned existence. And in fact, the idea is that every experience is automatically structured in an approach, avoidance, ignorance manner, such that, we respond to things that we seek, we avoid things that are unpleasurable or painful, and we ignore things that we deem irrelevant to ourselves. And so every percept and action is utility-based with ourselves in mind. And you can already see here sort of the parallels, I think, to predictive processing. But in Buddhism, the idea is that this way perceptions and actions are automatically linked to three unwholesome roots, namely attachment, aversion, and ignorance. And these are thought to be unwholesome qualities that cloud our mind, because in the end they give rise to craving. And craving gives rise to suffering and dissatisfaction. And so Buddhism also says that there's a way out of this conditioned existence, namely through meditation. And so in this paper that I wrote together with my now former postdoc Ruben Laukonen, who maybe all of you know, at least some of you know, when he was still a postdoc in my group, he's now an assistant professor in Australia. We actually point out these striking parallels between how the mind is conceptualized in Buddhism, the notion of conditioned existence, and then the notion of the experience-dependent predictive brain within predictive processing. And we actually put forward that predictive processing as a unified theory of the brain may actually provide an overarching theory to explain the many effects that meditation has. And so meditation has been associated with many effects, like it can release stress, enhance your working memory, enhance your self-esteem, increase your attention, enhance knowledge retention, etc., etc. And indeed, in the West, meditation is typically seen as a method to enhance cognition, but there's not really an overarching framework for understanding how it may bring about all these positive effects. And in fact, very advanced meditators typically also report states of being able to induce states that in a sense can be called esoteric, where they do not longer experience a sense of self and time and space. And actually they claim that it's those kinds of selfless experiences that may actually be most transformative. And so, how do those fall into this picture of boosting cognition? when meditation is also associated with states of mind that are thought to be very transformative, but are actually not characterized by, regular cognition at all. And so in our paper, we put forward that predictive processing can provide this overarching theory that can explain both these changes in regular cognition, but also can explain some of these more esoteric effects of meditation, including loss of sense of self. And specifically what we put forward is that 3 main styles of meditation can be placed on a continuum, and that they progressively bring the meditator more and more into the present moment. So when you're really in the present moment, unaffected by what just happened in the past or what may happen in the future, there should be no effect of learning on current experience. And that's basically the claim that we make. And specifically, our core hypothesis is that these 3 main styles of meditation bring the practitioner gradually more and more into the present moment by progressively abating hierarchical temporal deep predictive processing through modulations of attention, so through modulations of precision weighting. And so these 3 styles of meditation that I've listed here, they are main styles of meditation that you find across the different Buddhist traditions. So you find them in Zen Buddhism, Theravada Buddhism, Tibetan Buddhism, but they're obviously umbrella terms. They do not do justice to the wide variety of practices that are out there. And also there are many other meditation practices that are also very important that actually are not included in this list. For example, compassion meditation. But these are also styles of meditation that oftentimes people in the West are familiar with. Focused attention meditation, probably all of you know this, is a concentrative style of meditation where you simply focus your attention on one object, oftentimes breath sensations. And whenever you notice your mind wandering, you just gently bring your awareness, your attention back to this object of attention. And so how can we think about this in terms of predictive processing terms? Well, if attention comes down to precision weighting, you can say that in focused attention meditation, you upregulate the precision assigned to, in this case, then the breath sensations. And because you assign such high precision to this one object of attention, that automatically reduces the precision assigned to whatever else may pop up in mind. And so that should reduce the frequency of, but also grasping onto other mental processes. So it should reduce, for example, mind wandering, because you assign so much precision to this one source of present moment experience. And that should result in a shift from thinking to sensing. And indeed, the idea is that with advanced practice, one is no longer engaged primarily in this narrative self, mind-wandering mode of experiencing, but in this less abstracted present moment mode of experiencing. And then typically, once one has calmed the mind through focused attention meditation, one moves on to open monitoring meditation. Mindfulness, you could say, also falls under this category. And there one drops the object of attention and you simply open yourself up to whatever occurs in experience, be it a thought, a feeling, a sensation, but importantly, without following up on it, without judging, without responding. And so you could say that in open monitoring meditation, what you cultivate is a form of bare attention. It's non-selective. Everything is assigned equal importance. So if you think about this again in predictive processing terms, everything is assigned equal precision and consequently low precision because nothing is assigned importance. And so we've talked about when prediction errors, when mental responses are given low precision, they cannot penetrate deeply into the processing hierarchy. And so it should reduce also how we respond to things, sort of secondary responses. There's the thought, but it reduces the subsequent evaluation. And so as a function of open monitoring, the idea is that non-judgmental observing increases, where you just simply have things arise and go, and that the system then may begin to experience a kind of, what is called pure sensing without evaluation, without this secondary judgment. And that pure experiencing is conceivably also temporally prior to evaluations of the sensory experience. And typically what's being reported by meditators is that, you know, when they sit still for many hours meditating, they can start to experience excruciating pain, for example, in their back. That can then suddenly simply be dissolved when they realize that there are actually sensations coming from the back during sitting meditation that are then conceptualized by the brain as being painful. And, you know, then they can just be with those sensations, but not with the subsequent judging of it as painful. And so non-judgmental experiencing can be considered an experience at an even earlier level of the hierarchy, so temporally less deep. And so when we think about what I just said now, you know, in focused attention meditation, by focusing on the breath, you prevent your mind from engaging in these habitual modes of thinking and feeling that normally otherwise dominate our mental landscape. And then in open monitoring, one further reduces habitual responding by assigning less precision to whatever occurs in experience. And so through mental inaction, you could say, you prevent yourself from mentally acting in habitual ways. That should then lead to a weakening of these habitual ways of thinking, feeling, responding, attending. And that may also contribute to some of the clinical benefits of meditation. But there's actually this third style of meditation, non-dual awareness meditation. This is considered a more advanced form of meditation. It's also less well known, I think, in the West. And basically in non-dual awareness meditation, one aims to discover an awareness that allegedly always is there in the background. So it's said to be the ground of all experiencing. And it's always there, but we typically are not aware of this awareness because it's hidden by the ordinary structures of cognition. And so in focused attention meditation and open monitoring meditation, there's still embedded within the practice this duality. There's still an observer observing some object or sensing. But in non-dual awareness meditation, this duality between subject and object is also seen as a conceptualization of the brain that should be dissolved, because that then allows one to have to experience this pure or non-dual awareness. And this pure non-dual awareness is characterized by, I didn't really explain this yet, by this loss of sense of self, loss of sense of time, loss of sense of space. And to sort of explain this, because I think from a traditional cognitive neuroscience perspective, sometimes this is very difficult to understand. I really like this example that John Donne actually gives in one of his papers about seeing a teacup. So even a direct experience of seeing a teacup demands this complex process of construction from past experience. We only know that this is a teacup because we've interacted with it in the past. And seeing the teacup also automatically includes anticipation of possible changes in the sensory input related to being able to interact with the cup. There's this automatic elicitation of some affordance of what you could do with the cup. And we also talked about, as soon as you start to think about potential futures, how you can change your own sensory input, that automatically also ties in this sense of self, this basal self model that we talked about. And so actually within some Buddhist tradition, the idea therefore is that by realizing that our sense of self, subject and object, always co-arise in experience, we can actually sort of release any abstraction away from the here and now by just releasing also this very temporally shallow, this direct experience, this direct experiencing. And so if you can resolve this also, this duality, one should be truly in the present moment. And if one is truly in the present moment, any conceptualization and intentionality should fall away. There should be no influence of the past on current experience, and also no anticipation of future states. And the experience of timelessness is then actually a logical consequence, because if you're really just in this moment, the current moment is no longer situated with respect to the previous moment or next moment in time. And so then timelessness is a logical consequence, right? And there should also no longer be a sense of self, because if you're truly in this moment, when there are no expectations of future states, also this basic self-modeling should disappear. And so then your sense of self should also disappear. And so to summarize our basically theory, we propose that these specific styles of meditation gradually reduce temporarily deep hierarchical predictive processing through mental inaction, and actually also through physical inaction. Typically, you also sit very still. So there's no active inference, but there's also no mental active inference. And we propose that this can not only explain changes in regular cognition that occur during meditation, but it can also explain how we can, how certain advanced practices can induce these states where also our sense of self disappears. And ultimately also the emergence of pure awareness. And we also point out in our paper that what then is maybe the most important effect of meditation actually occurs off the cushion, because during meditation we prevent our brains from engaging in these habitual modes of thinking and responding by assigning very low precision to them. And so what may happen during meditation is actually these deep canals, that there's actually this flattening of the hierarchy of this attractor landscape. And that then off the cushion allows you to think also in other ways to become more cognitive flexible. And sort of to bring it also together with the first part of my talk, I really like this model by Kalina and colleagues, which is called the dynamic thought framework. And basically it's proposed that our thoughts can be structured in a two-dimensional way. One dimension is the extent to which thoughts are deliberate. So goal-directed thought is very deliberate, whereas creative thinking is less deliberate, mind wandering becomes more spontaneous, and dreaming is most spontaneous. But next to these deliberate constraints, the second dimension concerns automatic constraints. And so what is very nice about this framework is that it says that even deliberate processes can be automatically constrained. And when we think about what I talked about, attention, how your goal-directed attention can suddenly start to behave in certain ways based on predictive learning, the idea is here that you move up this dimension, and so you get goal-directed thought that is automatically constrained. The same thing for mind wandering. Mind wandering is very spontaneous. But if spontaneous thought becomes too automatically constrained, you actually get rumination and obsessive thought. So rumination and intrusive thoughts are not spontaneous anymore because they're also automatically constrained thoughts that behave in specific ways, that make you think and think, recurrently in the same patterns. And in a more recent paper that is now in press in biological psychiatry, Linacre actually postulates that what focused attention and open monitoring meditation do is actually reduce these automatic constraints on human thought. And that's, of course, very similar to what Ruben and I proposed in our paper. And so that we can get away from rumination and obsessive thought and enhance cognitive flexibility, the ability for our thoughts to operate more freely in more spontaneous ways. So I think this is a very nice framework for thinking about deliberate thought that can still be automatically constrained, or spontaneous thought that can also be automatically constrained and then can also become dysfunctional. The other thing that our framework, I think, can explain well are negative side effects of meditation that fortunately over the past, several years or so have also been getting more scientific attention. In particular, these enduring distortions in the sense of self. So quite a large percentage of practitioners or people who practice meditation also report negative experiences. For example, that after meditation, they cannot really get back into their body. They feel like they're floating above their body, or they feel they cannot really connect to their emotions. They're not really their own emotions anymore. Depersonalization, basically. And, if predictive processing plays such an important role in how we model ourselves. And if there are these radical changes in one's sense of self, that can generate a huge prediction error during meditation practice, that then changes your model of yourself in such a way that it's no longer sort of adaptive of the meditation cushion. And that can lead to these enduring distortions in the sense of self. So it's good that there's more attention for this, because then hopefully there's also more ways that we can actually prevent these negative effects from happening, or actually treat them afterwards. So what about empirical predictions and support? So in our paper, we talk about several predictions that our framework makes. And I'm not going to talk about all the predictions and empirical support. You have to read the paper. But I'll just present you findings from basically 2 studies that we've done that I think can nicely be accounted for also by our framework. And so sort of a main prediction 1 in the paper, is that the temporal depth of mental activity reduces from focused attention to open monitoring to non-dual meditation, and thus that neural activity should decrease basically across the temporal hierarchy across meditation styles, and ultimately also affecting temporally shallow, I don't know where it says thick here, temporally shallow mental processes such as conceptualization and our sense of self. But it starts with focused attention meditation. And so the idea is that we can assign high precision to one object of attention such that, that is what we're continuously attending to. So it should be associated with enhanced sustained attention, but also this should reduce engagement with spontaneous thinking that may otherwise dominate our mental landscape. So it reduces mind wandering. And when I was still a postdoc with Richie Davidson, we actually also did some studies looking at the effects of meditation on sustained attention. And this is a very nice paper if you're interested in reading it, whereby we actually look at the consistency of the phase of neural oscillations as induced by basically a train of auditory stimuli that's being attended. And we find that this phase consistency, so basically the temporal jitter in the brain's responses to stimuli that are attended, becomes less variable. And so that means that attention was really much more focused consistently on the object of attention. This is a recent paper that shows that meditation can, it's a review basically paper that shows that meditation can reduce mind wandering. Then open monitoring meditation, the idea is that the style of meditation creates this form of non-selective or bare attention where everything is assigned equal precision. And so a consequence of that should be that it reduces mental acting, judgment, evaluating, and thereby increase present moment awareness. And to show some evidence for this, I just want to discuss some findings from a study that I also did as a postdoc in the lab of Richie Davidson, because I still think this provides the nicest illustration of this. So in this study, we looked at the effects of people going into a 3-month meditation retreat where they practiced open monitoring meditation for 10 to 12 hours per day. And they also did some focused attention or shamatha meditation, but the vast majority of time was spent in Vipassana or open monitoring meditation. And I did not know much about meditation at the time, but when I was described what open monitoring meditation does, namely that it cultivates this form of non-reactive awareness, I immediately had to think about the attentional blink task. And so in this task, people are presented with a very rapid stream of stimuli, 10 per second, but embedded in the stream are always 2 target stimuli. So in this case, the 2 numbers. And participants have to identify these 2 numbers because at the end of the sequence, they have to report them. And what research has shown is that, interestingly, when you present the second target very rapidly in time after the first one, within half a second, your attention blinks to the second target. You often miss it, you don't perceive it. And the idea is that you don't perceive it when you don't perceive it, that is because your attention got stuck on the first target stimulus. And back then, there was a little bit of evidence from that by ERP studies that showed that when you look at this one ERP component called the P3B, which is an ERP component that is associated with perceptual decision-making, basically higher level processing of a stimulus, it seemed that this T1 evoked P3B ERP component was larger in amplitude in the trials where people missed the second target stimulus. So when you intentionally cling to a stimulus, then you may not be able to pick up on a new stimulus if it occurs while your attention is still with the previous stimulus. And so when I was described that open monitoring meditation cultivates this form of non-reactive awareness, I thought, well, if people then practice that for 3 months, it should reduce capture by the first target stimulus, and so increase one's ability to see the second target stimulus. And this reduction in T1 capture should be reflected in smaller T1 elicited P3B. And so we set out to test this hypothesis, and we not only tested this retreat group before and after their retreat, but also a novice group that expressed this interest in learning about meditation, and that we also tested twice with a 3-month period in between, but they only received 2 one-hour meditation instruction classes, and then were asked to meditate for up to 20 minutes in a week leading up to each testing session. They were free to also meditate in the 3-month period in between, but they did not have to. But even if they did, the amount of meditation they did was much less than what the people did in this intensive retreat. And so we had them do an attentional blink task while we recorded their EEG, both before and after. And I was a little bit nervous about this. This was my first study I did in meditation. I associated it mostly with religion still, but I also thought if you do something systematic with your mind, it should change how you process information. But on the other hand, it also took about a year to collect all this data. And I remember thinking, oh my gosh, if this doesn't bear out, I will have wasted a year of my postdoc on this meditation study. But it bore out precisely as predicted. So we found that the particular practitioner group showed this selective increase in the ability to see the second target stimulus at time point 2 compared to the novice group. And we found that only in the practitioner group, there was this reduction in the T1 evoked P3B over time. So this reduction in brain resource allocation to the first target stimulus. And in a further analysis of this data set that we published in a second paper, we also looked at the brain's ability to pick up on this second target stimulus. And so we again here looked at the phase of oscillatory activity and found that in response to the second target stimulus, it became less variable in time. And that's also in line with the idea that if your attention is less stuck on the target, but more in this moment, your brain can just respond to a new stimulus right away. And there's less variability because you're just there to respond to it. So that's what we found in this paper. So I think this is a nice study because, first of all, it suggested that the attentional blink does not reflect an immutable bottleneck in information processing, which has scientific value. But also it's in line with this notion that open monitoring meditation may reduce the propensity to cling to events and increase present moment awareness. And so I think it illustrates both the scientific value of meditation in a scientific study of attention and consciousness, but also the value of neuroscience for better understanding how meditation may work. And then in non-dual meditation, our prediction is that even processes that are temporally prior to appraisal and judgment related to perceptual categorization, for example, should disappear. But how do you do research on a state like that? Because that's, of course, a huge challenge, because during these deep meditative states, you cannot ask participants to perform some task, because that automatically takes them out of the state, because then they have to make decisions and select actions, engage in predictive processing, in other words. And so, how do you study this? And so I just, for those of you who are interested, want to draw your attention to the MPE network, which was established by Thomas Metzinger. He's a philosopher, and it's a network of scholars and scientists that all sort of try to better understand what characterizes this state of non-dual or pure awareness. It's also called the minimal phenological experience. How is this state initiated at the computational and neural level, and how can we understand it also at the phenomenological level? And Thomas actually published a book, The Elephant and the Blind, that reports on the experience of over 500 meditators and their experience of pure or non-dual awareness. And it's actually open access on MIT Press. So if you're interested to read more about it, I can really recommend that book. But in any case, how to study these deep advanced meditative states, not just non-dual meditation, but also very advanced open monitoring states, where you simply have to take note without judging. There too, you cannot ask people to perform some sort of task, because then too, they have to engage in decision-making, action selection, etc. And so one of the ways in which we try to tackle this in my lab is to work with no report paradigms and then combined with neuroimaging. And what is a no report paradigm? Basically, you present stimuli to the brain of participants, but they don't have to do anything with them. And then you just look at how the brain responds to them. For example, to regularities that you introduce in the input. But the example I want to give today is something we're still working on. So it's preliminary, but I think it's very interesting. And so it concerns a no report binocular rivalry study, where we look at the effects of focused attention versus open monitoring meditation. And so binocular rivalry, I don't know to what extent everybody knows what that is, but it's a very interesting phenomenon that occurs when you present each eye with its own input. So via special contraption or glasses, one eye, for example, only sees a face and the other eye only sees a house. That's very different from how we normally perceive, because normally things in the world, come in through both eyes. So the veridical input when you have one eye seeing a face and one eye seeing a house is actually a mixed percept, a mixed house-face percept. But that is not what our brains or what you subjectively perceive. You either see the house or the face. And in fact, our perception rapidly, every 2 to 4 seconds, alternates between seeing a face and a house. Can we think about that from a predictive processing perspective? Yes. Because we have a strong prior for a face, we have a strong prior for a house, but not for a mixed house percept. And so what our brains do is they infer, I'm seeing a face, but there's also the house input, triggers a prediction error, and then you get a flip, oh no, it's a house. Can explain the house input well, but not the face input, prediction error, oh, I believe I infer it's a face after all. And so you circle back and forth between these two interpretations of this input. And so several years ago, there was this study that was done by Olivia Carter. She's a consciousness researcher, where she went into the Nepalese mountains and visited very advanced monks in caves and had them do this binocular rivalry task wearing these particular goggles. And one group of monks was very experienced in a style of meditation called one-point meditation. That is also related to keeping things stable, concentration. And these monks reported that they could keep one percept stable for very long periods of time, exceptional long periods of time in some of these cases. But what's also mentioned, but in the supplementary materials, is that these monks opted not to report on what they were seeing during the binocular rivalry task, because that took them out of the state. And so they reported on it afterwards. But we also know that, subjective reports can be unreliable. How do you know that you had a percept for 37 seconds in mind? In particular, during such an advanced state that may also alter your perception of time. And so we thought we should replicate and extend this study using a no-report binocular rivalry paradigm. And when Ruben was still in my lab, we actually started developing this no-report binocular rivalry paradigm. And we presented our participants with these two stimuli that we also had flickering at different rates. So they were flickering, I don't know what the frequency is here, but in any case, they were flickering at 2 different rates. And we did this because we concurrently measured EEG. And you can find this flicker frequency back into visual signals that we record with EEG. So you see huge power, for example, if you flicker at 6 Hertz, huge power at the 6 Hertz frequency. And a lot of work has shown that when you attend to a particular stimulus, when it's flickering like that, that it enhances the amplitude, the power of that we measure at that flicker frequency, versus when you don't attend to it. So what we did was with EEG, we continuously tracked the power in these 2 frequency bands, 2 frequency peaks, you could say, over time. And that is shown here. So here you see time in seconds, and here you see power. And here in blue, you see it for one of the 2 stimuli, and in red, you see it for the other one. And you can already see, looking at this, that they seem to be in counterphase from each other. And here in the background, these bands reflect what the subject saw. So red is they saw, well, I call it the red stimulus, but one of the two stimuli, stimulus A. And here they saw the blue stimulus, stimulus B. And you can see when the participant reports stimulus B, there's this increase in also power at the blue frequency. And you can see there's pretty good alignment, maybe a little bit of a delay here. And so what we found in this study here, we just did it with normal participants, not meditators, that when we looked at the number of perceptual switches that people self-reported at the behavioral level, and the number of switches, perceptual switchers, that we guesstimated just based on these neural activity traces alone, so no report, neural data, that we found this very strong alignment, very strong correlation. And so we thought, well, this is a good no report paradigm to take to meditators. But we also saw that our neural measure overestimated the number of switches a little bit compared to the self-reported switches. And there were some other things we noticed that we thought we can actually do better. And so we not only took this paradigm to the meditators, but we also improved on it methodologically. And I'll just talk about that in a second. And so Surya Selvan, he's a PhD student that Ruben and I co-supervise. He's currently running this study. We still have 2 participants to collect. So I think we have the data I show you still on 21 participants. And so we have these very advanced meditators come to the lab for 2 sessions. In both sessions, they first perform a binocular arrival task while reporting on their perception, but also in a no report condition where you're just simply looking at the stimuli, but they're not reporting on their perception. And then in both sessions, after they just do it without meditation, like a baseline condition, they actually engage in an audio-guided meditation. And in one session, it's focused attention, and the other session, it's open monitoring meditation. And then after they've done that for 10 minutes, they actually are being presented with the arrival stimuli first, and no report blocks, and then self-report blocks. And so in the focused attention meditation condition, we instruct the participants to just take this concentrative state to the task and to keep whatever percept they have in mind stable. And our prediction here is that that should lead to longer percept durations, that these advanced meditators are going to be able to keep these percepts stable for a long time. This would, in a sense, be a replication of what Olivia Carter showed, although I think her meditators were even more advanced than ours. And in open monitoring meditation, the instruction was to also take the meditative state to the task, but to simply be aware of all aspects of experience without judgment. And so the idea here was that this should shorten percept durations because one doesn't assign high precision to either percept, and maybe even lead to more mixed percept, to more veridical perception, because that's the veridical input, right? Not structured by top-down beliefs. It's just a mixture of the 2 inputs. And so that's what we did. And so here you see the behavior during the self-report blocks. I'm sorry if it's a bit small, but I'll talk you through it. On the left for the focused attention meditation session, here you see self-reported percept durations in the baseline condition, and here in a focused attention meditation condition. And you can see that there's a significant difference in percept durations. And there are in particular a few meditators that report exceptionally long percept durations, really long. This one is almost 100 seconds long, which is very exceptional. You don't find it in normal people. So the idea is that this would also be at the neural level reflected by longer percept durations. But also in an open monitoring meditation session, we find significantly longer self-reported percept durations. And we had predicted that we would find shorter percept durations, but we also had predicted maybe that there would be more mixed percepts. And you can imagine that when there are more mixed percepts, it may also take longer to transition from one percept to the other. So before you report that you're seeing another percept. So maybe these slightly longer percept durations during open monitoring meditation reflect more mixed percepts. And this is something we can get at by looking at the neural data. And when you directly contrast things to each other, we see that there's no difference in baseline percept durations between FA and OM session, which is good. But we do see a difference between focused attention and open monitoring meditation, such that the self-reported percept durations are longer in focused attention versus open monitoring meditation. So the methodological advance that I told you I would tell you about is actually that we added a localizer task to our study design. And in this localizer task, we only presented one of the flickering stimuli at a time. So left eye flicker, right eye flicker, left eye flicker, right eye flicker. And then we trained a multivariate classifier on this signal that we measure at the flicker frequencies and how it varies over time to tell us from the pattern of brain activity what percept a person was seeing. Was it stimulus A or stimulus B? And then we applied that classifier, we tested it to the self-report blocks. And this is something that's ongoing, so we've only just started doing this, but it seems to be working very well. So here you see for one participant, when we trained the classifier on the localizer task, but then tested it during binocular rivalry in the baseline self-report block, you can see, well, first in the background again, what percept the person reported. So stimulus A is white, stimulus B is red, stimulus A is white, stimulus B is red. And so you see this alternation in perception. But what we plot on the y-axis is the confidence of the classifier in that participants were seeing stimulus A, then it's a 1, versus stimulus B, then it's a 0. And you can see an almost perfect alignment with this red trace, which is the classifier confidence, in what the classifier says, just based on the neural data alone, what the participant was seeing and actually what they were reporting. But you can also see there's some deviations. For example, here the person reports seeing the other stimulus, but the classifier only goes back to, okay, yeah, there's maybe a change in percept, but then it quickly goes back to the other stimulus. So maybe this was more of a mixed percept that never went full blown, but nonetheless, the participant pressed a button that there was a switch in percept. Is the classifier accurate or is the subject self-report accurate? That's the question. But the interesting thing is, we also had some participants that already in their baseline data self-reported exceptionally long percepts. So maybe there's also some trait differences that sneaked into the baseline. And basically here you see the data from this other participant, and you can see they first reported this one stimulus for more than 15 seconds, then briefly the other one, then this one again for 7 seconds, and then they reported for almost 50 seconds that they only saw this one stimulus, no switch. And look at what our classifier says. Our classifier actually says, yeah, there was a really long percept duration here, a briefer one here, then something that's more of a mixture. And then here, there was clear evidence at the brain level that there was only this perception of this one stimulus. Here, it seems the classifier says there was a perceptual switch, although it never became fully confident. And then it quickly went back again to that same percept for basically the remainder of the block. So I think this is a very nice illustration of how a no-report paradigm combined with brain imaging may actually be able to tell us what can happen during these deep advanced meditative states that would be disturbed by having to press buttons and make classifications. And so, to be continued, it will be really cool to see what happens during meditation when we apply classifiers also to these no-report meditation blocks. And see whether indeed we find more mixed percepts in open monitoring meditation. That would be when our classifier sort of hovers around the 0.5 point here. It's not one stimulus, but also not the other one. All right, so that does bring me to the end of my talk. Thank you for your sustained attention so far. So I think the main points I wanted to make is that learning is a much more pervasive feature of mental activity than we traditionally assume in mainstream cognitive neuroscience. And in fact, Helmholtz already said that it may be impossible to completely and sufficiently demarcate how extensive this influence really is. But what I've hoped to show is that meditation may provide a useful method to scientifically study and modulate also the plasticity of the predictive mind, and to reduce these automatic constraints on thought. And that may actually be its value for human flourishing. And so with that, I want to thank all the people that contributed to the ideas and work I presented here today. And of course, you again for your sustained and learned attention. Yeah, thank you.
That was really quite a tour de force. So I'm sure there are questions in here. I've got my computer here so I can see if there's a question online as well. So if you have a question online, please raise your hand. Maybe we should start here. I'm sure there's some questions.
Shamil?
That was an amazing talk. There's so much rich ideas and materials. Like, I wanted to ask you something that you didn't talk so much about, but was there in the background, which is about pure awareness and what the kind of frameworks that you presented could tell us about what's going on in pure awareness states.
Yeah. Yeah, so basically I've mostly described what falls away in the state, right? So these ordinary structures of cognition fall away, sense of time, sense of space, sense of self. But what meditators report, and this is also something that Thomas Metzinger, for example, emphasizes in the book, is that what really remains in the state is this sense of wakefulness and epistemic openness. And so he has actually proposed in some work that maybe we should think about the state of pure awareness as a Bayesian model of tonic alertness. And so in many meditation practices, one also regulates their arousal levels, right? You shouldn't be too dull or too overexcited. And there's always this level of arousal in the background. If we are not alert, not aroused, basically we fall asleep. And as we awake, arousal reemerges, and that actually provides the conditions for our brains also to respond and perceive and stuff like that. And so basically he says that that may actually provide a predictive processing explanation for the state of pure awareness. Actually quite sympathetic to that idea. Yeah. Yeah.
That's great. I mean, I love that. And the one thing is like, this is again something you haven't mentioned, but what happens to arousal in a cessation then? Does it just go down?
It's a very good question. Yeah. I mean, you were there when I presented the findings from our cessation study with a very advanced practitioner who induced a state for 90 minutes. And we also measured physiological variables like heart rate, respiration rate. And we didn't find significant changes or very abnormal changes in these physiological variables. One explanation for that could be that, even though cessation, when somebody does it for a long period of time, is this low metabolic rate, is associated with this very low metabolic state, it may take time to sort of drop into that. And of course, talking about neural alertness is different from talking about bodily arousal. And so that may be an important distinction as well.
So the particular activating system might shut down or something.
Yeah. But it's not aching like deep sleep. So what is the difference? Yeah. And in the talk that I gave in Bamberg, the idea was that maybe because states of cessation also preceded and followed by states of minimal physiological awareness, they are functionally related to each other. And the question is the state of awareness, the state of cessation really a state of unawareness? Or is it an even more minimal form of awareness where we just lose this ability for, how do you say that, episodic personal level memory recall afterwards? Yeah. But yeah, it will be good to chat more about that. Yeah, it's interesting. Yeah.
Other questions in the room? Let's see if we have somebody online.
Yeah.
Thank you. That was really interesting.
Yeah.
I'm usually 100% mind wandering up here, but that was I was there. So thank you.
Yeah.
Would you mind going back to the binocular rivalry paradigm, just the most recent one? I think. Yeah, this one.
Yeah.
So the examples on the right hand side. So
down here when it has the quotes from.
Oh, this, yeah.
The button presses influence my perception of the image. Would you mind discussing what's happening there? So is it like?
Yeah, so I didn't really talk about it, but we also had questionnaires where we asked people to describe their experiences. For example, also self-report on percept durations, or how if they saw a lot of mixed percepts and how often. But we also asked them a little bit to talk about the extent to which they experienced they could control percept durations and some of their phenomenology. And one of the questions was indeed, because we had no report and self-report blocks, we also wanted to ask them just about to what extent they felt having to report on their experiences actually hampered their ability to apply the meditative state to the stimuli. Yeah, but I don't talk about that now. We also haven't fully analyzed those data yet because we're also still collecting some data. Yeah, yeah.
I mean, I think, if I may ask, I mean, I think it was wonderful the way you started with your interest in attention and about egocentric attention, and then how you then moved on to these other states, yes?
Yeah.
What's next for you? What are the kind of questions that you would like to further investigate? Now you sort of move from a very focused kind of attention to much more interesting states where there's no attention. Is there no attention in cessation?
Well, no regular attention, at least.
And what does that mean in terms of the ego?
Yeah, exactly. I mean, how are those associated, right, with each other? Yeah. No, I mean, I think when we think about that two-dimensional plane with deliberate thought constraints and automatic constraints, we know very little about how these automatic constraints are placed upon deliberate thought processes. We can see that, learning about statistical structure in the world, or how you can sample information in the world, that it automatically makes your attention behave in a certain way, that there are these sensory biases. But how does that work at the neural level? And so I would be really interested to look at that, and to also look at also at the internal level, when our internal attention gets constrained automatically by how our attention internally has behaved in the past. How that may then also happen at the level. So sort of more seeing how we move up the automatic constraint dimension, I think would be very interesting.
Yeah, I guess the space-time evolution of that.
Yeah.
I always get very worried when they're just two axes and things. But,
rightly so.
And I think what's really interesting, and I think what is very interesting about the way that your research has gone, is really been about that. It's about unfolding that in time.
Yeah.
Because I think really what we're talking about here is not a two-dimensional system, it's indeed a three-dimensional. Because
there's experience.
And I think that really interesting thing where you deliberately train your mind to focus or not focus on certain things, that then allows these processes to run their natural course.
Yeah.
I think that, and the personalization of that, and does that just rely on your prior experiences? Does it rely on your anatomy, if it was connectivity, and how can that change? Now, the final question I want to ask before we need some coffee, real good coffee, as you already had, maybe too much.
And chocolates, right?
Absolutely. And some food, of course, because we need more food, I think. So you didn't really talk much about psychedelics.
No.
At all, in fact.
I actually don't do any psychedelics research.
You don't have to.
No.
But what I'd like to for you is maybe to speculate based on what you've thought about. We spoke a bit about it before the seminar. We talked about how some practice meditators say that it actually helps them unlock some of those states. I mean, to what extent do you think that speaks to that? Do you think really, again, thinking about your automatic and deliberate things, is that really what's going on here?
Well, I mean, of course, you're all familiar with Garrett Harris, right? And how he thinks about psychedelics, and how, in a sense, you could say it loses these automatic constraints on experiencing. And so maybe something similar happens there as in these more advanced meditative states, whereby guidance by top-down beliefs is just.
So we've done some more rather Celine Assasoy, former postdoc of mine, who's now still doing research. She's been looking at the similarities in terms of the harmonic framework, which is really unfolding the space-time. priors, you could call them, but really
Yeah.
harmonics. And what
Yeah.
you find is that these two processes, whether you use the classical psychedelics or you use in experienced meditators, they are
Yeah.
very similar in some aspects, and in other aspects, very, very different.
Fascinating. I don't know.
And again,
that.
I think that's
Yeah.
something that we should probably talk about, and we should
Yeah.
think about, and we should maybe even think about, especially from a hierarchical point of view.
Yeah.
I think that's another thing you're very interested in.
Yeah.
So yeah, no, I think there's plenty of
Yeah.
exciting things we
Yeah.
should do and talk.
Yeah.
But should we maybe perhaps thank Helen again for her wonderful talk?
Yes.